Today we are going to listen to Dr. Justin Bray give a talk about how the geomagnetic field and the atmosphere protect us from cosmic rays. Dr. Justin is an esteemed IAU member, and he is a research support scientist at the Jodrell Bank Centre for Astrophysics in Manchester. Some of his early work is using the Parkes radio telescope in Australia to detect fast radio pulses caused by high energy particles hitting the moon. And some of his work now is basically, his research revolves a range of techniques using radio astronomy, sorry. So please please join me in welcoming him today. Thank you for being with us, Dr. Justin.
No worries, thank you, Fatima.
Thank you. For the listeners, please note that we will be dedicating the last 15 minutes for a quick Q&A session with Dr. Justin. So you may do so by writing it in the chat or raising your hands, and we will be taking turns asking questions. So without further ado, Dr. Justin, you may begin.
Okay, thank you, Fatima. So I'll just add that I joined the IAU last year, so this is my first time doing something like this. Feel free to give me a nudge if there's something you'd like to have more information about. Okay, is everybody seeing this?
Yes.
Excellent. Yes, welcome. I'm going to give you a sort of a blend between things I work on specifically and so know some minutiae about and a more general overview of cosmic rays and high energy particles around the Earth and its environs. So I'll be going through these topics roughly in this order. I'll talk just briefly about who I am and what I do, a bit about the early history of cosmic rays and how they were discovered, some of the things we've learned about cosmic rays since then, the way they move in magnetic fields, and a bit about the environment of high energy radiation like cosmic rays around the Earth itself. Myself, as Fatima said, I did my PhD at Parkes Observatory in Australia using the lovely 64-meter antenna you see on the left there. As she said, I used to try to detect radio pulses from high energy particles hitting the moon. The bit she left out is that I didn't see any. I'm reasonably confident, though, that we did the experiment completely right, and the reason we didn't see any is that they weren't there. That is, we managed to show that there weren't enough particles with enough energy to see from this distance, which was enough to rule out some ideas of how high energy particles might be produced. So this is the way science frequently progresses. You have many small negative results to close out the wrong theories before you eventually find the right ones. So where I work now is the Jodrell Bank Observatory in the UK, which has this primary 76-meter radio telescope you see in this picture here, and 6 smaller telescopes that together are used as an array. About half of my work is operating this radio telescope on behalf of astronomers around the world. So the way it works is if an astronomer anywhere has a project they would like to do with a radio telescope, they apply for time on these instruments, and we record the data for them to analyze. But I also work in cosmic rays, developing a set of cosmic ray detectors like this one here. You'll see me here. This is me deploying this second prototype at a observatory site in Australia. The first prototype is at Jodrell Bank for testing. The third prototype we tested in Germany recently. And so that part of my work is about building these to detect cosmic rays at ground level using what should be an array of 8 detectors by the end of this year. Okay, so now on a bit of history. So in the late 19th century was when scientists first identified what they called ionizing radiation. That is radiation which is powerful enough that it will ionize matter, knock electrons out of molecules or atoms. And through some experimentation, they divided this up into various forms, what they called alpha rays, beta rays, gamma rays. though they didn't know at the time exactly what these were. And they had instruments they could use to detect background radiation. And what they found was wherever they put their instruments, like these electroscopes, they could use them to, they would detect this background radiation. In some cases, they could say, yes, this thing is producing extra radiation, like, for example, uranium ores, pitch blende. They could detect extra radiation from that. But the background radiation everywhere, they weren't sure where it came from. And the two major contending theories at the time were, maybe it came from the ground, from all the Earth contains some background level of radioactive ores. And the other idea was maybe it came from the sky. So an experiment was done in 1912 to tell the difference between these two, and it's a wonderfully elegantly simple experiment. Somebody called by the name of Victor Hess took two electroscopes on a hot air balloon and then rode it up to about 5 kilometers altitude and recorded the radiation at each altitude. And the idea was, if the radiation levels dropped, then the radiation was coming from the ground. If the radiation levels increased, it was coming from the sky. And the answer was both. You see the radiation levels here drop slightly at first and then increase. So some background radiation comes from radioactive substances in the Earth, and some comes from space. And the component from space we call cosmic rays. So this was the state of knowledge in 1912. Since then, we have learned a lot more. We now know that these cosmic rays individually are very high energy electrons and nuclei. When one of them hits the atmosphere, it interacts with, given that the atmosphere is mostly made of nitrogen, it normally hits a nitrogen atom and smashes it to bits. And then those bits, because they together contain the energy of the original cosmic ray, and since it was very energetic, they have lots of energy too. And so those fragments of the nitrogen atom then hit more particles in the atmosphere, which then hit more and more. And so this is a artist's impression of a cascade from one original cosmic ray creating a cascade of more and more lower and lower energy particles. And so this is happening all the time, frequently. When these cosmic rays hit the air above us, they create these cascades reaching down to ground level with much of the energy being dumped higher up in the atmosphere. There are plenty of things we still don't know about cosmic rays, though, and the most annoying is the question of exactly where they come from. Because these cosmic rays are electrons and atomic nuclei, electrons have negative charges and nuclei have positive charges, so they are all electrically charged, which means in magnetic fields, they all follow curved paths. And if space is full of interestingly shaped magnetic fields, then if something is producing cosmic rays, they're going to follow some complex twisty path to reach us. And by the time they reach us, the direction we see them coming from is not where they originally came from. Now, we can get around this a little bit by looking at the most energetic cosmic rays, which follow straighter paths. So the more energetic they are, the less bendy their paths are. And if we just look at the most energetic cosmic rays and draw a map of the sky to see where they're coming from, we see that where they're mostly coming from is roughly where most of the extragalactic matter in the nearby universe is, which is and importantly, not from the center of our galaxy, which is a hint that these cosmic rays at least are coming from outside our galaxy. This is tricky though, because these high energy ones, at the very top of the spectrum we've measured, the number of these cosmic rays you get is only about 1 per square kilometer per century. And these most energetic cosmic rays, the usual comparison is that one of them has the same energy as a well-served tennis ball. So that's sort of thing. You can be hit by a tennis ball and it won't hurt a whole lot, but it's that amount of energy packed into a single atomic nucleus, a single particle, which is incredible compared to anything else we see in the universe. So for comparison, if you've heard of the Large Hadron Collider, which is a large particle accelerator in Europe, the maximum energy it can accelerate particles to is 6 times 10 to the 14 electron volts. We have seen cosmic rays up to over 10 to the 20 electron volts, or over 100,000 times as much as energetic as we can produce on Earth. So we have these models now saying what the flux might be. We have an effect we can by which we can explain why the spectrum, most energetic ones, should cut off around about this energy. We think these ones at these energies that we see coming from certain directions are extragalactic, and we have various models. They could come from active galactic nuclei, gamma ray bursts, or possibly from dark matter particles, or topological defects if those exist. At lower energies, they are more likely to be galactic in origin, coming possibly from supernova remnants. But this is all the very top end of the cosmic ray spectrum. And these are individually very high energy, but those aren't the ones we're most concerned about from a radiation point of view. Now, the analogy I'd use to describe this is compare a racetrack with just a handful of very fast-moving cars versus a full highway backed up for kilometers with tens of thousands of cars. In this case, you have a small number of cars, each with a very high energy. In this case, you have a much larger number of cars, so that even individually they have less energy. Altogether, they have more total energy than the race cars. So these are the ultra high energy cosmic rays. These are the more normal cosmic rays, which are less energetic, but more numerous and contain more total energy. So when you look down to the less energetic ones, the bottom end of the cosmic ray spectrum merges into the solar wind, which is a stream of high energy particles being emitted by the sun. And these, as I said, the higher energy ones are less deflected by magnetic fields. The lower energy ones are more deflected by magnetic fields. Now, our Earth has its magnetic field, which you know if you've used a magnetic compass, the needle points towards magnetic north. And it has if it weren't for the sun, it would have a nice dipole shape with these field lines circling around from the North Pole to the South Pole, like so. The stellar wind does tend to push and deflect our the geomagnetic field, the field of the Earth, out in this direction away from the sun. But in any case, it is strong enough that the particles in the solar wind don't just go through it, they get deflected by it. And if you've done the bit of high school physics where you do the right hand rule to work out which way the force is on a charged particle, you can work out that the magnetic field tends to make them follow the magnetic field lines. So these high energy particles get trapped in the geomagnetic field and travel along the field lines, rather than penetrating through to the surface here, like the more energetic cosmic rays do. Now, by looking at this, you'll see that means they can approach the surface of the Earth near the North and South poles. And if you've heard of the auroras, the aurora australis and aurora borealis, that's what causes these. When these high energy particles enter the atmosphere near the North and South magnetic poles, they ionize molecules in the atmosphere, and as those lose that energy again, they emit light at certain characteristic colors. And so we see these lovely displays of light in the sky. This is a shot, I think, from Estonia, which is fairly far north, enough so to see the aurora on occasion. This is a satellite picture of the aurora from above over Antarctica, and you can see it forms a ring, because this is a ring of the area on the surface of the Earth where these field lines intersect it. So these less energetic particles from the sun are trapped in the geomagnetic field until they are funneled towards the surface of the Earth around the magnetic poles. Now, these particles that are still trapped in the geomagnetic field, they form what we call the Van Allen belts. So these are belts of high energy particles trapped, traveling along the field lines away from the surface of the Earth. And they form several separate belts because they get divided up by the mass of the particles. The higher energy ones can penetrate more. Sorry, the higher mass ones can penetrate more than the lower mass ones. That means the protons and the electrons get separated out. And so this means that for the lower energy particles, we are protected on the surface of the Earth from exposure to the radiation from them. And astronauts in low Earth orbit around the equator are also protected. But if you are in a polar orbit that travels through the poles, like some satellites, they get exposed to a burst of radiation each time they pass through the Van Allen belts here and here. And also, if a satellite or probe or astronaut goes outside the Van Allen belts to higher orbits, then as they pass through them, they're exposed to an additional dose of radiation. So in summary, cosmic rays are these high energy particles from a range of sources we haven't identified all of yet in space. They are a mix of electrons and various atomic nuclei. They are deflected by magnetic fields, particularly the low energy ones, which means that the Earth is protected from them by its magnetic field. And they are also blocked by the atmosphere. The ones that are high enough energy to penetrate through the geomagnetic field get stopped by the atmosphere, and only some of the radiation penetrates through to ground level. So on the surface of the Earth, we are generally protected from the radiation from cosmic rays, but they are still a concern for astronauts and for satellites or anything being sent into space that could be vulnerable to radiation. So thank you very much for listening.
Thank you, Dr. Justin. That was quite informative. Anyone, guys, if you have any questions, okay, we have a question here from Sarah Khan. She's asking, how did people realize that radiation was actually real?
Okay, so that's a good question. The different types of radiation were detected in different ways, but the most basic scientific way that you tell that something is real is you do a controlled experiment. So for example, X-rays were detected because they would fog photographic film. So in the early days of photography, I think around about the 1890s, they had photographic film they could use to make pictures. But if they exposed them to X-rays, then the film would fog up. So what they would do is they could, and at the time they were producing X-rays by, I'm not sure if they had cyclotrons at that point, but they had some means of producing X-rays. So the way they could tell this was real was to take two samples of photographic film, put one of them in front of the machine that makes X-rays and turn it on, then off again, and then leave the other one at a distance. And then afterwards, look at the two pieces of film, and they see that the one that was in front of the X-ray machine has been fogged up. So that tells you that and the other one hasn't. And that tells you that there is something real. Whether you call it radiation or something else, that shows that there is something producing this effect, which since they weren't sure what it was at the time, they called them X-rays, for X for unknown. And since then, we've learned more about what they are, but that's how they originally could tell that there was something real. Does that answer your question?
Yeah. Yeah, great.
We always some people doubt that there are astronauts actually went to the moon because of the because of the radiation, the Allen belt, and all. What's your opinion regarding that?
That's a good question. So I said that yes, it is more dangerous for astronauts who go to beyond low orbit, and it's because they pass through the Van Allen belts. And yes, the Apollo astronauts are the only people who have ever been outside the Van Allen belts. The simple answer is they passed through them fast. They made sure that their orbit from the Earth to the moon went out at a high speed, straight through the Van Allen belts quickly, so they didn't get too much radiation exposure. Now, once they were outside the Van Allen belts, they were no longer protected from the background solar wind, which means that firstly, they picked up quite a significant dose of radiation from that trip. So this, I think somebody worked out the numbers, and they maybe have the Apollo astronauts maybe have a very slightly elevated risk of cancer over their lifetimes, but not enough that you would turn down going to the moon on the basis of it. But the danger was the sun sometimes suddenly becomes more active and produces a burst of the solar wind with a much higher radiation dose for a few hours. And if one of those had happened while the Apollo astronauts were in space outside the Van Allen belts, that would have been quite dangerous. What they did, I believe, is the sun goes through an 11-year cycle between being more active and less active. So I think they timed the Apollo missions to happen during the low activity stage of the solar cycle. And we can also sometimes get some warning of when the sun is about to flare. But it was still one of the dangers that the Apollo astronauts faced.
I was gonna ask, like, is there a way to detect like low energy, like burst of particles from the sun? But you answered my question already. Yeah, we have a question as well. Sarah, this is a follow-up question to Sarah's question, is how did people get to the idea of radiation? How was it communicated that there is this thing that we can't see, but it can affect us and we can sense it in many other ways? Like, how was it translated to the people?
Well, originally they didn't know how it had affected us, which led to some unfortunate cases in the early history of experimenting with radiation before they realized that it could be dangerous. I think the idea that radiation could be used to make X-ray images of people's bones was discovered very early on. I think I've seen a picture of an X-ray of someone's hand from, I think, from the 1900s, I think, very soon after the discovery of X-rays. And so I think this was probably the way through which the general public learned about high energy radiation, the idea that you can form X-ray images to see broken bones. I'm not sure of it, but I think that's the way it became generally known.
We have another question from Ban. The question is, can artificial magnetic fields be generated and used to protect spaceships and satellites?
Good question. I'm not sure. In principle, I think the answer is yes, but you would need quite a strong field. I've seen suggestions of doing the equivalent with an electrostatic field, where you just put a large charge on your satellite, which has the minor disadvantage that if you put a big positive charge on your satellite, it will slow down positively charged cosmic rays coming towards you, but it will accelerate the electrons because they're negatively charged. Yeah, the short answer is I don't know. Maybe. I suspect the answer is probably yes in principle, but it would be too heavy to put on a satellite. But I'm not sure of that.
Does anyone have any more questions?
I would like to ask
Yes.
about the.
Yes, please.
You can go ahead, Ali. It's fine. Go ahead.
Okay, thank you so much. It's my pleasure to talk to you, Doctor. Just I have a question. Why the cosmic ray is important for scientists to it's important to scientists to accept to discover the new phenomena in the universe.
Sorry, why it's important for why? So you're asking why scientists are interested in discovering what about cosmic rays?
Yes, yes. Why scientists use a cosmic ray to discover a new phenomena like black holes or others?
So the simple answer is usually it's something we don't completely understand yet, and so we try to figure out everything else about it. But there are several things we can learn about through cosmic rays. So I listed several possible sources of cosmic rays. If we were able to pin down cosmic rays to one of those types of object, that would tell us a great deal about that type of object, because we would know that it must have certain conditions inside it to be able to produce cosmic rays. For example, I mentioned one of the possible sources of cosmic rays was topological defects, which are some hypothetical sort of knot in space-time that might have been created soon after the Big Bang. And if they existed, we should have seen more cosmic rays at the very top end of the spectrum. And we didn't, so those topological defects probably don't exist. But if we had spotted them, then that would have told us something very strange about the way space is organized on small scales. So that would tell us, I think, something about how microscopic black holes might form. And at the other end, ignoring the question of where cosmic rays come from, you know that physicists operate particle accelerators like the Large Hadron Collider to see how particles behave when they collide at very high energies. Cosmic rays have even higher energies than we can produce here on Earth, and they're interacting in the atmosphere. So if we look at one of these cascades in enough detail, we may be able to learn things about how particles behave at very high energies that we can't learn from particle accelerators because we don't have powerful enough ones yet.
I have a question. Hello, it's
Yes, please go ahead.
yeah, sorry. So I was just saying it's an honor to be here in this webinar and to participate. So I had a question about radiation. As I know, radiation is also present in microwaves. So why don't the companies like lower the amount of radiation, and what is like the typical amount of radiation found in microwaves? And like how much radiation can consume, or does it affect us like by using it in our daily lives?
Okay, so there's an important distinction I have to make here, and that's between high energy and low energy radiation. So have you heard, I guess you've probably heard of at least some of radio waves, infrared radiation, light, X-rays, gamma rays. Together, these make up what we call the electromagnetic spectrum. Basically, they're all the same type of thing. They're all different forms of light. The only difference is how short their wavelength is. And visible light that we see is in the middle of that spectrum. And in one direction, you get high energy radiation like ultraviolet light, X-rays and gamma rays. And the higher end of that is what you can get produced by interactions of cosmic rays. And those are ionizing radiation that when they interact with us, they can cause mutations, cause cancers and so on, which is why, for example, X-ray machines, they are quite careful about what sort of dose they use, because they want to be careful not to give somebody the risk of cancer. The other direction, though, from visible light, not the high energy direction, the low energy direction, you go through infrared light, also known as heat radiation, microwaves and radio waves, and those are all lower energy, and so those don't harm. They cannot harm someone by causing cancer. They don't. The individual photons don't have enough energy to change a base pair in a DNA molecule. So a microwave oven, if you do everything exactly wrong, if you carefully sabotage it so it will operate with the oven open, then you stick your head inside it, then you may be able to cook your head, but you will not be able to give yourself cancer. In fact, if you look at the door of your microwave, you'll see a wire mesh. You see, it's not just a plain glass panel. There are lots of little holes. That mesh is there to keep all the microwaves inside. It wouldn't stop high energy radiation, but from microwaves, it keeps it all inside so that it doesn't cook anything outside the microwave. I think that probably partly answers your question, but if you want to choose any bits of it you'd like more information about, feel free to ask.
I believe Miriam had a question as well. Miriam?
Yes, my question is, we hear from time to time about the Earth magnetic field that it's going to flip. Is it accurate, and is it going to flip soon?
That question is way outside what I know about. You probably know about as much about that as me. I mean, I understand the basic story that we see evidence for these magnetic flips in fossil strata by looking at the orientation of magnetic minerals. And I understand the magnetic field, the north and south magnetic poles wander over time, and people track those. What actually causes the flips, I don't know. I'm not even sure if anybody does know. But we can ask the question, what would happen if the Earth's magnetic field did disappear for a time?
Yes.
And in that case, let's see, cosmic rays would still be being stopped by the atmosphere, but they would no longer be concentrated at the poles by the magnetic field. So we wouldn't get the auroras anymore, or rather the auroras would be evenly spread over the whole atmosphere, so we wouldn't see anything. And low Earth orbit would become somewhat more dangerous for astronauts. On the surface, I don't think it would affect us much because we'd still have the atmosphere.
Okay, I have a question.
And if we lose the atmosphere, we have bigger problems.
Okay, I have a question. You were saying that the cosmic rays, because we have a magnetic field, it causes ionization at the north and south pole. So, is it scientifically, or I don't know if this question is like very accurate, but is it dangerous to be living in those areas for a long time, or to be exposed, let's say, to the aurora or whatever phenomena is caused there?
I think that there is a good question. In terms of your background radiation level, I think the biggest effect is just whether you happen to live in an area with lots of granite, I think, tends to have a high background radiation count. So the fraction of your background radiation from the ground matters more than the background fraction from the sky. Near the poles, I'm not sure that anybody lives far enough. Certainly, I know people who have spent a year plus at the South Pole, and they were okay. A bigger effect, I think, is from your altitude, because the higher energy cosmic rays ignore the Earth's magnetic field more or less, and the higher you are in the atmosphere, the more of them you're exposed to. Very few people live at high enough altitude for this to matter, but when you're on an aircraft, you can get a significant extra dose. So I think if you work out the numbers for people who spend a lot of time at high altitude, so pilots and airline staff, they get, I think, a few percent more background radiation than the average person on the surface.
Thank you. Does anyone have any more questions before we wrap it up? Oh, okay.
Sorry, Victor, I think you're muted.
There's a question. Is the magnetic field radiation harmful? And can you explain as well?
Sorry, the magnetic...
This is a question from Jihan. She says, is the magnetic radiation harmful? And can you explain that as well?
Okay, so the magnetic field is not itself radiation. We have the Earth's magnetic field, and it just affects the movement of the cosmic rays, which can irradiate us. Now, the magnetic field is not harmful. It's enough you can detect it with a magnet, but it's not enough to have any significant effect on us. In fact, for some medical instruments, for magnetic resonance imaging, people are exposed to far higher magnetic fields than the geomagnetic field, and it doesn't cause them any harm. But ionizing radiation, so the high energy end, ultraviolet, X-ray, gamma ray, those are harmful in that they can have the risk of creating cancers. And cosmic rays, when they interact, generate gamma rays that can have that effect. I think that answers your question, but feel free to ask a follow-up if you have more.
Could I ask a question? Is there any difference between the North Pole and the South Pole as regards radiation?
I don't think so. Certainly all the effects I described, the way that particles travel along the field lines, though for both positive and negative particles, they could end up at either the North or the South Pole almost equally easily. The one thing that could cause a slight difference is if the Earth's magnetic field is not quite symmetrical. So if the magnetic field is slightly more spread out at one pole compared to the other. And that is probably the case to a very small extent, but I've seen that in the magnetic field of a star I was looking at, but I don't think the Earth's magnetic field is significantly different between the North and South poles. So the end result is, yes, the Aurora Australis and Aurora Borealis should look pretty much exactly the same.
Thank you.
Bon, you can go ahead and unmute and ask if you'd like.
Yeah, okay, thank you. Hi. So my question is, I think it's a two-part question. First of all, based on the observations that we have, is the direction that we get the cosmic radiation from isotropic, or do they come from a certain direction in the universe more than the other?
Okay, shall I answer that part and then you give me then you ask the second part?
Yeah, please.
Okay, so the answer is they are almost isotropic, but with some interesting differences. So you saw one of those slides I showed you was of a map of the arrival directions of the very highest energy cosmic rays. And those, slightly more of them arrive from one particular part of the sky compared to the rest of the sky. And that direction corresponds to where there are quite a few nearby galaxies. And it is not the same as the direction of the center of our galaxy. So if these cosmic rays were coming from the center of our galaxy, you would expect more to come from that direction than from elsewhere. The fact that that doesn't happen is hints that they are extragalactic in origin. Now, if you look down towards lower energy cosmic rays, it becomes more isotropic. They're coming from very, very nearly around the whole sky equally, because at lower energies they are deflected by magnetic fields around our galaxy, and so that mixes up the directions. But then, if you look at very low energies, they are coming from the poles of our magnetic field, because the geomagnetic field guides them around that way, and they enter the atmosphere near the north and south poles. So that's an anisotropy. What was the other part of your question?
Do we take the planning of, let's say, space probes or spaceships, satellites, when we plan their paths for any journey? Do we take the cosmic radiation into account, where it comes from and how intense it is?
Where it is and how intense it is, yes. So computers on spacecraft are generally radiation hardened. There are several ways of doing this. One of which is to have, the simplest of which is just to have several redundant systems. So if a high energy particle happens to hit one computer chip while it's doing a calculation and it produces the wrong result, you have another 5 that are all giving you the correct result. So that sort of thing allows the satellite to do computation reliably, even when it's in a high radiation environment. And the amount of effort that goes into this radiation hardening depends on where the satellite is going to go. If it's in a equatorial low Earth orbit inside the Van Allen belts, it doesn't need very much radiation hardening. But if it's on a polar orbit or it's going outside the Van Allen belts, then more effort goes into radiation hardening its electronics.
Okay, that's really interesting. Thank you.
Okay, do we have any more questions, or should we wrap it up?
Sorry. Can I ask one more? Oh, sorry. You can ask.
Go ahead. Go ahead.
Oh,
Go ahead.
okay. Sorry, I'm just like kind of excited for this webinar. It's kind of I'm feeling excited. So my last question is as we know, magnets are made out of different materials, such as the temporary magnets also and permanent magnets. Like a permanent magnet could be aluminum, nickel, and cobalt mixture, and then a temporary magnet. So how does if we change the materials in the magnet, how does it change the magnet field? Do the materials have a change in the power, like attraction or something?
Okay, you're testing me here because this is physics that I should have learned in my undergraduate degree, and I think I've forgotten most of it. I know that different materials have different levels of ferromagnetism, I think is the characteristic that lets them retain a magnetic field. And that different additives to an alloy affect this in different ways. And that certain rare earth elements can form very, very powerful permanent magnets. The Earth's core, I think, is a mix of iron and nickel, which can form a permanent magnet. But I've also read, just skimming over this, this is outside my field, so don't pay too much attention to me, that the Earth's magnetic field is associated not just with permanent magnetism on the part of the Earth's core, but with the flow of material within the liquid outer core of the Earth. And that as a consequence of this, planets that have had enough time to cool down so their core solidifies all the way through, like the moon, don't have a significant magnetic field. I'm not sure if I answered your question or just danced around the edges of it, but I hope that was helpful.
Okay, now my turn. Okay. Now we know that Mars' atmosphere is thinner than the Earth, and of course, so the radiation, the cosmic radiation, hits Mars more than the Earth. So, how bad is it in comparison?
As far as cosmic rays are concerned, the atmosphere of Mars may as well not be there. The important characteristic of the atmosphere for this sort of thing is the column density. That is, if I imagine a tube going from sea level up to the top of the atmosphere, what will be the mass per area of the atmosphere? And for Earth, that is about 1,000 grams per square centimeter. And that is enough that a vertically interacting cosmic ray, the cascade will quite comfortably reach ground level. An inclined shower, which has a larger column density because it's going sideways through the atmosphere, will sometimes be stopped before reaching the ground. The column density of the atmosphere of Mars is, I don't know the figure offhand, but I think it's less than 1,000th that of the Earth. So most cosmic rays hitting Mars will probably reach the ground without interacting with the atmosphere at all.
Last question, please. I have the question about the color of aurora. Why is it green, always green? And is a difference between a planet and other planets or not? Or it's always green?
Oh, that is a good question. It is, even on Earth, it is different colors. So I said that the aurora happened when a molecule in Earth's atmosphere is hit by a high-energy particle, which knocks an electron out, which means ionizing it. When that electron recombines and drops down to its previous energy state, that loss of energy is lost as a photon of visible light. And the amount of energy the electron lost determines the color of the light. And the amount of energy the electron loses between two different energy levels depends on what molecule it is. So the color of the aurora depends on the type of gas at the altitude in the atmosphere where this interaction is occurring. So on Earth, depending on the altitude, the aurora may be forming from high energy particles hitting nitrogen molecules or ozone, or I think monatomic helium at different levels in the atmosphere, and each of those will have a different color. And on another planet, it may be one of those colors or another one altogether, depending on what gases are present in its atmosphere.
Thank you so much. Thank you.
I think we have a question here as well. It says, how can you explain how solar sail technology works?
Okay, so confusingly, a solar sail is nothing to do with the solar wind. The way a solar sail works is it uses the fact that light has momentum. So the sun produces light, and the light hits us and pushes us. Now, it does so very, very weakly because it doesn't have very much momentum. But if you have a mirror sitting in space where there are no other forces acting on it, and the light reflects off it, then it will be pushed very slightly. And if you wait for a few weeks, it'll be pushed gradually faster. Now, if you want to get much force out of this, you have to make sure your mirror is very light. So the ideas for a solar sail usually involve, I think, a very thin film of plastic with a coating of aluminium, just so you can get the lightest possible mirror. But if you can make a very light mirror and have many square meters of it, and angle it in the right direction, then the sunlight will push you. And this is very useful in space where If you don't have a solar sail, then you need to use fuel, and getting the fuel to the spacecraft is very expensive. So a solar sail is a slow but potentially very useful under certain circumstances.
Any more questions before we wrap up? I think we have 5 minutes left. Okay.
Well, I have a quick question for people here then. If in your stargazing, do you often get satellites passing through your field of view?
We do. We have, like, Mariam and I went stargazing in Jordan, Wadi Ram. We've captured a lot of images with satellites passing through. Also in Amman, like on top of a 3-kilometer mountain. It was quite visible. We actually saw it with our eyes, and then we were able to capture it using our cameras. So yeah.
Have there been more of them in the last year or so? With I'm thinking in particular of the Starlink satellite deployment. If you've heard of this.
Yes, I've heard of the Starlink, but the last year we haven't had many stargazing sessions because of the pandemic. But hopefully in the future.
But we have noticed the Starlink for sure. We can see them. And we even track them. Like some of our members tracked more than 4. For me, I've tracked only 3. I saw 3. Unfortunately, we couldn't see that. On the internet, you can see them like more than 50, 60 just passing in the sky. But yeah.
Yeah, so for us in radio astronomy, they are mostly not a problem, except if we happen to be looking at the same frequency as they're transmitting, in which case they're suddenly very, very loud.
Ali says we've also spotted many in Hawar. He's right, we have. Hawar Island is a small island, a part of Bahrain. We go there for our stargazing trips, and we have actually spotted many satellites passing by. He says we didn't know what they were initially. We thought it was just like an unidentified object, but yeah. All right, I think we don't have any further questions. I would like to thank you, Dr. Justin. Thank you so much for a very informative session.
No problem. Thank you very much for the chat. It's been fun.
It is a pleasure speaking to you. Thank you everyone for joining us today. So I guess on this note, we will be signing off. Have a great day, everyone. Thank you. And yeah, good night.
Good night, everyone.
Good night.
Thank you.